Routing is the term used to describe the transfer of network traffic from one network to another one. So if routing is allowing data transfer from one network to another network, what's a router? Well, in the vast majority of cases, especially in large companies, routers are dedicated hardware devices. But our Windows 2008 server itself can also function as a router. So let's say that you're sitting here at home, you're in your home little network there, and you're connected to the internet via cable or maybe a DSL connection. It's likely that you could have the device that handles your connection, we'll say that's DSL here, is also likely to be a router. Now, it's this router that connects two networks together and allows data to be transferred to and from each place. So, to our home network over here, our home PCs, and out over the internet. So, let's say that you're at home on what would be a typical home network, and even if you only have one computer, it's still arguably considered to be a network, by the way. It's just only one device on that network. So on your typical home network, you're going to have a home computer that's going to be using an IP address, and that'll look something like 192.168.1.2 for argument's sake. And therefore, our router, the device that sits between our home network and our internet service provider, would have an internal IP address of something like 192.168.1.1. Now, since these two IP addresses here, 192.168.1.1 and 1.2, are on the same network, this allows both of these two devices to talk with each other. However, when your computer here, this IP address here, when this wants to go and access something outside its own network, for example, a website on the internet, now it needs to go outside our local network via the only way it knows how, and that's by sending the data to its default gateway, or in other words, sending it to the router. So on our router, we've got two interfaces, two network interfaces. Our first is connected to our home network. This is the one here with our 1.1 address. And the second, however, is connected to a different network. In other words, our internet service provider. And obviously, these are the guys that provide us with our internet connection. So our second network card inside our router would be connected to the internet. Let's just draw it out here. This is our second network card. It's going to be connected to the internet using a totally different IP address, which we call a public IP address. Now, this public IP address allows our router to be contacted by any other host on the internet. Now, a business network really doesn't differ much from what we've just looked at with regards to our home network. Sure, they probably don't use DSL routers to connect to the internet. They'll have something a little bigger and a little faster, and they probably won't have one computer on their network. They're probably going to have hundreds or even thousands of them. But the basic premise is the same though. We could have, let's say we've got a couple of hosts here. There's a couple of computers on our business network. That's going to connect to our router. And of course, in turn, that's going to go out to the internet. So for argument's sake, we'll use the same IP addressing scheme here. We'll say this host has an IP of 192.168.1.2. This one has 192.168.1.3. Our internal interface on our router is going to have 192.168.1.1. And our external interface obviously needs to have a public IP address, and that'll be something like, say, 200.240.5.5. So when we look at our home network here and our business network, obviously we're still talking about the same technology, the same functionality. All of our hosts on this side here of our network, on our internal network, they're all on the same subnet. They're all on the same network. So they can talk to each other without the need for any routers. But once any of these hosts on our internal network need to talk to a host on a different network, now whether that's a host out on the internet or a host on a different subnet, such as a branch office computer in another building or another state, then that communication will need to be routed by our router, of course. Now, in a moment, we're going to see how we can configure a Windows 2008 server so we can use it as a routing. But first, let's just talk for a short moment about the different types of routing. Well, we have a couple of different types with Windows 2008. We can talk about static routing, and we can talk about dynamic routing. Now, with our static routing, this is where we'll manually set up and we'll configure and we'll manage the router ourselves. Now, we're going to need to maintain our routing table, but with dynamic routing, on the other hand, we've got specific routing protocols that pretty much manage all this stuff for us. Now, this allows for new networks to be discovered automatically and routing tables to be updated automatically as well. Now, Windows 2008 also supports both the Routing Information Protocol, or RIP, and the Open Shortest Path First, or OSPF, routing protocols. And a little later on in this video, we're going to see how we can implement dynamic routing. So in my lab here, I've got a Windows 2008 server that has 2 network cards in it, because remember, you need at least 2 network cards in your server for it to be able to be a router, because each card is going to need to connect to a different network. So in my lab here, let's just draw our server. That's our server here, and we've got 2 network cards. One is connected to our 10.32 network with the IP address of 02. And on this side, we have a network card configured with the IP address of 10.64.0.2. So obviously, both of our IP addresses, both of these network cards, are pointing to different networks. So by making this Windows 2008 server into a router, we're now going to have hosts that are on this 10.32 network, that's a 32 there. They're going to be able to talk to hosts on our 10.64 network. But before we go off and we start making this server a router, it's a good idea, firstly, to ensure that this server is at least able to contact a host on each side of the network that it's connected to. That way, it makes troubleshooting easier later on, since we'll know first up that our server does work and it can talk to devices on each side before we install anything else. So with that in mind, the first thing I want to do is go and test our server and just make sure that it can in fact contact devices on this network and on this network here. Okay, so here we are on our Windows 2008 server. So to test our machine, to make sure we can in fact connect to devices on both of those networks, we're going to open up a command prompt. And we're going to ping, first of all, a Windows Vista, I think it is, machine that I've got on this network, 10.32.0.10. Let's try that. We'll hit enter. All right, and we can see that that ping is successful. So let's go and ping a different host, this time on our 64 network. So we're going to ping 10.64.0.10. All right, and that comes back as successful as well. So now that we know that our IP connectivity, the basic IP, is working, we're now ready to set this machine up as a router. So firstly, we're going to install the routing feature, and then we'll configure a static route. So to do that, we're going to fire up our server manager. We're going to choose roles. And over here on the right-hand side, we're going to click Add Roles. Now that's going to start up the Add Role wizard. And the role that we're looking for is this Network Policy and Access Services role. So we're going to click that, and we'll click Next. Now I'm going to skip this introduction to Network Policy and Access Services. You can read that if you like. There's nothing else we need to do here except for clicking Next. Now we'll need to select the role service that we want to install, and that is going to be the Routing and Remote Access Services. So we're going to check this box, then we'll click Next, and finally we'll click Install. Now this is going to take a few moments to install this role service, so I'm going to pause the video and come back in a moment. Okay, we're done. The role's been installed successfully, so we'll click Close. All right, now we'll click Start, and we're going to go to our Administrative Tools, and we're going to launch the Routing and Remote Access console. And probably the first thing you're going to notice about this console is that we've got this red downward pointing arrow, which indicates that our server isn't yet configured. So we're going to right click on our server, and we're going to choose the very top option to configure and enable routing and remote access. Now when we select that, that's going to fire up this wizard, so we'll click next. Now you can see that we've got quite a few options here, and some of these we're going to talk about in other videos, but obviously this video is all about routing and configuring routing on Windows 2008. So the option that we'll want to choose is going to be the last one, the custom configuration. So we'll choose that and select next. And now you can see we've got 5 options here, but again the one that we want is down the bottom. So we're going to choose LAN routing and we'll click next. And we'll get a basic summary of what we've done, which is to set up this router, or this server rather, as a router. So now we'll click finish. Okay, well we're told that our routing and remote access service has been installed. So do we want to start the service? Well, it's not going to be a working router until we do start the service. So yes, we're going to click start service. And that routing and remote access service obviously is going to be started and initialized. Okay, well, everything's started and we can see that that red arrow we had has now changed to a green arrow, indicating to us that everything is now running. Now at this point, we've now set up routing between our 2 networks, our 2 network cards, of course, which on my server point to the 10.32 and the 10.64 networks. So if we go and expand IPv4, and then we select General, in the right-hand side of this console, we can see we've got 2 network interfaces in this machine, a local area connection and local area connection 2, with the IP addresses of 10.64.0.2 and 10.32.0.2. And these 2 IP addresses were configured by me before we installed this machine, obviously, as the router. So at this point, if you've been following along with your own machines, you can go ahead and try out your router. Now we already know that this machine, our router, is able to ping at least hosts on each side of its network, both on our 10.32 network and our 10.64 network. But can other hosts on each of these networks talk with hosts on their opposite network? Or in other words, could I get a regular Windows Vista machine, for argument's sake, that's on this 10.32 network, directly communicate with another Windows Vista machine on our 10.64 network, and vice versa? Okay, well let's find out. Now I've just connected to a Windows Vista machine here, which happens to be in my 10.64 network. So in order to see if this side of the connection is working, let's go and open up a command prompt. And firstly, let's just run an ipconfig/all. And up here we can see that, there you go, 10.64.0.10 is the IP address of this machine. So that clearly puts this machine on our 10.64 network. So if we try and ping our router's internal interface firstly, so we're going to try and ping 10.64.0.2. We shouldn't have any problem getting there because obviously that network card on our router, on our Windows 2008 server, is obviously on the same network as this machine. But in order to truly see that our routing's working, we're going to want to ping something on our 10.32 network. So why don't we try and ping the other Windows Vista machine that I've got on my network, which has an IP address of 10.32.0.10. All right, now that's responded fine, telling me that packets are leaving this machine. They're heading to our Windows 2008 router on its 10.64.0.2 interface. That machine identifies that these packets are for a machine on the other network, so it's passing them across, or rather, it's routing them to that network where they can now contact the machine at 10.32.0.10. So what we should find is that the reverse should also be true. We should be able to jump on our 10.32.0.10 Vista machine and ping this one just as easily. So real quick to be sure, I've just connected to our other Windows Vista machine here, which is on my 10.32 network. So let's verify that this side of our connection is working fine. Now let's just ensure that I am on the right machine. Let's do an IP config. All right, we've got 10.32.0.10, so we're on the right side. So now let's try and ping 10.64.0.10. And obviously that's responding fine. So we know that really just by installing our routing and remote access role, we've already got a router that can route traffic between our 10.32 and 10.64 networks. Okay, well that's routing. It's easy and it works. But unfortunately, it only gets more complicated from there. You see, in a very small environment where you only have a couple of subnets, most people are going to be happy with what we've just achieved. But in a large network where you've got 2 or more routers, well, we've got some choices. We can implement static routes, set it all up manually, or use a routing protocol for dynamic routing. Now let's quickly take a look at static routes first, and for that, we will need to switch back to our router, but first let's stick here at the whiteboard because it's definitely easier to learn this stuff now here when we can visualize it rather than just looking at the console, and we'll get back to that in a moment. So what we're going to do here is we're going to assume for a moment that we've got this fictitious network, and within this network we've got 4 subnets. So on subnet number 1, this is going to be we're going to call this our New York subnet. And this is going to be on our 10.32 network. Next, we're going to have our Paris network. And that's going to be in our 10.64 subnet. Now over here, we're going to have our, let's say, a Sydney network. And that's going to be in our 10.96 network. And over here on the far right, let's say this is London. And that's 10.128. So each of these locations around the world has its own subnet, and they're all connected by these big black squares, which are our routers. We'll call them router A, router B, and router C. So what this means is that in order for, say, New York over here in the far left to be able to communicate with Paris, any communication will need to be routed from this 10.32 network through to the 10.64 subnet via router A. Now this is called a hop. It's one router hop away from the destination. Now in order for any user on our New York subnet here to be able to communicate with a user on the Sydney subnet, this data needs to pass through 2 routers. 1, 2, and so this becomes 2 hops. Now, I will point out though that this first part of the network, the New York section, we've already actually built. We've already got this router. We've got router A built and configured, and we've arguably already seen a host in New York, let's say our 10.32.0.10 machine, communicate with a host in Paris, which was 10.64.0.10. So with our 2 Vista machines, we've already simulated our network of New York communicating with Paris. But what if we wanted to extend that network to include Sydney? Well, if we choose to use static routes, which is what we're going to look at first, we'd need to do this all manually. So why don't we quickly go back to our Windows 2008 server and let's set up a route to Sydney. Now I will point out though that in reality, anything from router B onwards, this section onwards here, I really don't have that hardware in my lab. So let's put on our make pretend hats and let's assume that I do actually have router B sitting in my lab and it's already got 2 network interfaces in it. So we're going to theorize here that we have 2 network cards obviously in this router, one with the IP address of 10.64.0.3, and obviously that's connected to the Paris network, and on the other side it's going to have an IP address of 10.96.0, let's use .3 again. Obviously this is connected to the Sydney side. So what we'll need to do first of all is to tell router A over here that in order to get anything over to Sydney, it first needs to send packets out via its 10.64 network interface for it to be able to reach router B on its 10.64.0.3 interface. Now we can do that by simply configuring a static route. Okay, well, we switch back to our Windows 2008 router. So over on the left-hand side, we're going to click Static Routes. And in here, you can see currently that there is nothing there by default. There's no static routes being defined. Now, we already know that our router here can pass packets from our 10.32 subnet to our 10.64 subnet and vice versa. So now we'll need to configure this router with a static route so it's able to forward packets out to the Sydney network as well. So to do that, we're going to right click on static routes. We're going to choose a new static route. Now, one of the problems you're going to have here is selecting the correct interface. Now, I've only got 2 network cards in this server, and already I can't remember which one I need to work with. Is it local area connection 1 or local area connection 2? Well, actually, it's not really all that hard for me to simply click cancel here, go back to general, and locate the correct network card here by looking at what IP address is assigned to it. But there is a better option, which really only takes a minute, and that's to rename these connections. So we're going to click Start. We'll go to Network, Network and Sharing Center. I'm going to choose to manage our network connections. All right, well, here's our 2 connections. So I'm going to select our first one, Local Area Connection. I'm going to choose to rename it, or just simply hit F2, same thing. I'm going to call this one 10.32, and let's just call it New York. That's good. And we're going to do the same, hit F2. And I'll call this 10.64 Paris. Okay, and that's it. Now let's close these windows. We don't need them open anymore. And we'll go back to our console and refresh it. And now we can see our network connections have been renamed. And now it's really easy to identify which connection we're dealing with. So let's again click Static Routes. We'll right click, choose New Static Route. This time from our drop down list, it's much easier to pick the right network interface. Now, if you recall back to our diagram, we want to set up a static route from our Paris network to our Sydney network. So we're going to choose Paris here. Now, the destination is going to be 10.96.0.0. That's the network we want to connect to. The IP address, the network mask is going to be 255.224.0.0. And the gateway that we're going to use to get to this network will be the router's interface of 10.96.0.3. Now, as for this metric field, this field's where we can set the cost associated for this route to reach the destination. Now, this generally means how many hops will it take to get to this network. So I'm going to change this to 2, and we'll click OK. All right, so that's how we can add in a static route using the GUI. And we can also do it from the command prompt as well. So let's just quickly go and see how we can do that as well. So let's just right click on this route we've just added, and we're going to choose to delete it. And we're going to go back to our command prompt here. Let's just clear the screen. And we're going to type in route print. And let's hit enter right now. And what this is going to show us is what our current routing table looks like. This is a list of all of the places that this router knows how to get to. So if you are testing things out and you're wondering why things aren't working the way you think they should be, you can use this route print command to find out. Now, if you don't see a route to the network that you think you should be able to get to, then obviously that's most likely to be the problem. In fact, you don't actually even need to use the command prompt to find out this information. If we switch back to our console real quick and right click on static routes and choose to show our IP routing table, you can pretty much get back the same information from this GUI. Okay, so let's go back to our command prompt here. And to add in a static route, we're going to use the route add command. And let's add in that route again real quick, which is 10.96.0.0. That's the network. We'll need to add in a mask of 255.224.0.0. The interface that we'll need to connect to get out to that network is going to be 10.64.0.2. And I think it's actually 3. We'll soon find out if it doesn't work. And the metric will be 2. So here we're going to be adding in a route to our 10.96 network using this network mask and going through our gateway here using the metric 2. So we'll hit enter. And since we didn't get an error, we can be sure that our static route was added. So to view our route table, we can now simply type in route print again. We'll hit enter. And if we scroll up, we should be able to see here that our route has been added. Now, we are going to run into a problem when we decide to reboot this server though, because this new route that we just added is going to be lost. because unlike when we added a route via the GUI a moment ago, unless we explicitly tell this route command, then the route is not going to be persistent. Or in other words, it'll only be here until we reboot, and then it's going to be gone. So to make this route hang around after we reboot our server, or rather to make it a permanent route, firstly we'll go and delete this old route by typing in route delete and then adding in the IP address of 10.64.0.3. We'll hit enter there and delete that. Now let's add back our route again, and this time at the end we're going to add in a -p. So we'll hit enter there, and now if we type in route print, and now you can see here it's listed under this persistent routes section. So if we decide to reboot this server, it'll be back when our server is back up and running. All right, well, that was pretty easy, but you can imagine how much work's involved in a more complicated network with a whole bunch of routers and a lot more subnets. Now, if that's the case in your network, it's really unlikely that you're going to want to muck around with static routing. There's just too much to do and too much to manage. So this is where you're going to want to take advantage of using routing protocols with dynamic routing. So let's quickly do a route delete and get rid of that static entry so we can move on to our dynamic routing section. Okay, so to configure our server to use dynamic routing, back in our console, we're going to right click on General, and we're going to choose the second option, New Routing Protocol. Now we've got a few options here, but the one that you want to concern yourself with is the bottom one, RIP version 2. So we're going to select that. We're going to click OK. And over here on the left-hand side of our console, we'll see we've got this new menu item called RIP. And if we select that, you'll see here on the right-hand side of the console that we don't have anything to show because RIP hasn't yet been configured to use any of our interfaces. So let's go and take a look at our configuration options. So the first thing we'll need to do is to tell RIP that we want it to use a particular interface. So we're going to right-click on RIP. We're going to choose New Interface. In our network, we've currently got two interfaces, our 10.32 New York one and our 10.64 Paris networks. So let's choose Paris for this example, and we'll click OK. Now this brings up the configuration options we have for RIP on this interface, where we've got 4 tabs: General, Security, Neighbors, and Advanced. So our first step is to configure which mode of operation that RIP will use. Now the default is to use a periodic update mode, and that means that RIP is going to send its routing tables to other RIP routers in our network at an interval that's specified on our Advanced tab here, and you can see by default that's 30 seconds. So in other words, every 30 seconds this router is going to tell other RIP routers about the routes that it knows about, the routes that it's learnt, so that way they'll also know about them. Now our second option is to use an auto-static update mode, and this means that our RIP router won't actually send out its routing table to other RIP routers unless they ask for it. Now these auto-static updates, they also differ from the periodic updates in that routes that are learned from other routers aren't added as RIP routes. They're added as persistent static routes, which means that if we reboot, the route will remain until we manually remove it. Whereas with our periodic update routes, these are refreshed as our network changes. Now our next section here is our outgoing packet protocol. The default is to use RIP version 2 broadcast. Now we've also got the option of using version 1 broadcasts, version 2 multicasts, and silent RIP. Now we'd use RIP version 1 broadcasts if you want to remain backwards compatible with older devices. RIP version 2 multicasts is used when we have all of our routers being registered for multicast traffic. We'll try and use this option if all of our devices support it. And finally, silent RIP is where our router is going to listen for broadcasts, but it won't actually send any out. So I'm going to leave the default here at RIP version 2 broadcast. And for the incoming packets, we've got similar options. We could use RIP version 1 and 2, which is the default. We could change this to RIP 1 only or RIP 2 only. Or we can choose to ignore incoming packets if we don't want to learn what our other routers know. Now the next section here is our added cost for routes, and here the default is 1. And what this means is when our RIP2 router tells another router about a route that it knows about, it's going to add 1 to the hop count. And this is because the router that it's updating will have to cross an additional router, this one in fact, to get to the destination. So whilst this router, this Windows server that we're on right now, might have a hop count of 1 to get to a destination, when it passes this information onto another router, it'll tell the other router that it's going to have a hop count of 1 plus this added 1, or in other words, a hop count of 2, which kind of makes sense. Hopefully that was clear. If it wasn't, let's just quickly fire up Paint here so I can sort of draw it and visualize it for you. Let's say we've got router number 1, that's this router that we're on right now, and we've got another device over here that this machine has just learnt about. Well, over on this side, it's going to then tell this guy, well, in order to get over here and talk to this machine, you have a hop count of 1 plus 1, which of course equals 2. So for this server or subnet to connect over here, it's 1. For this one, it's 1 and then 2. Hopefully that helps make a little bit more sense of what we were talking about there. All right, now tag for announced routes. This lets us mark specific routes for administrative purposes. And finally, we can also force our RIP router to authenticate with other routers by activating this authentication checkbox here and then providing a password. So whilst this can increase security because then rogue routers can't update our routers with bogus information, this authentication password is transmitted over the network in plain text, so it can be easily captured using Network Monitor. Okay, on our security tab, we're able to configure how we're going to handle both incoming and outgoing routes. Now for incoming routes, the default is to accept all routes, and this is going to have the effect of making our router listen to everything it gets and adding it to its own route table, making it bigger and bigger. But we can further lock this down by telling our router to only accept all routes in the ranges that we list, and then in these fields we can enter in the details of the subnets in our network. And if we do that, then our router will only accept incoming routes from any of those subnets. Now, alternatively, if we don't want to learn about routes from specific subnets, we can choose to ignore routes in the ranges listed and then fill in the details, click Add, and away we go. Now for our outgoing routes, we've got exactly the same sort of options, the default being for us to announce all routes, but we can also elect to only announce the ones that we list or not to allow the ones that we list in the fields below. Now on the third tab, the Neighbors tab, we can configure how this RIP router will interact with its neighboring routers. Now the default is to use broadcast or multicast only, but we can use unicast as well to direct our traffic to or from our neighboring routers. And if we select this option, it's going to open up these fields below, so we can enter in those details for our neighboring routers. Alternatively, we could use unicast instead of broadcast or multicast, and again, we'd then need to specify which neighbors that we want to talk to. Now finally, on the Advanced tab, well, we've already discussed the first option, which is the periodic announcement, and that is the interval in which our updates occur, which by default, as you can see, is 30 seconds. Now we can also specify the timeout before routes will expire. That defaults there to 180 seconds or 3 minutes. And what this means is that this router is going to cache a route that it's learned about for 3 minutes. And if it hasn't received an update about this route within 3 minutes, then it's going to expire. And then in another 2 minutes, it's going to delete that route from its route tables entirely. But one thing to keep in mind is that over here on this tab, if we happen to be in auto static update mode, then this setting here won't have any effect and the route will definitely not be deleted. Okay, next we've got the ability to enable split horizon processing, and this setting means that our router will not advertise a route that was advertised to it. And this is important because if we don't enable this, then we can get into routing loops. So let's say that we've got our two routers, router A and router B, and router A learns about our 10 network. So it goes off and it tells router B, hey router B, I've just found a new network, here's all the information I know. So router B updates its routing table with the new information that it was just given by router A. So router B, now that it's just learnt this information, if this split horizon processing is not enabled, if this was unchecked, it's going to then say, hey, router A, I know about the 10 network, so here's what I know. So router A is going to update its route tables with that information that it already knew, and then the whole process continues again. Now, the problem exists that when router A needs to forward real packets to the 10 network, well, what happens? Well, router A checks its route tables and it finds an entry for the 10 network. So it contacts router B to get to the 10 network. Router B says, oh, to get to the 10 network, you need to go through router A. So router A again checks its route tables. It's going to find that it needs to go through router B. So as you can imagine, this data never gets to its destination and we're stuck in this never-ending loop. All right, so that's split horizon. So what's the next one? Poisson reverse processing. Okay, well, let's say that router A learns about a route from router B. Router A checks its route tables and discovers that in order for it to get to that destination, it needs to cover more than the allowed 15 hops. So router A is going to contact router B and tell it that the destination is unreachable. So in effect, it says to router B, hey, I can't get to that destination, so when you tell other people about that route, don't tell them to come to me because I can't get there. So that's definitely something we should leave on. Enable triggered updates ensures that all of these routes are automatically sent out to other routers once a change has been made. It doesn't have to wait for the next update interval. We can send cleanup updates when we stop our router. And what that does is it enables this router to tell the other routers that it's being shut down and to clean up their route tables so they're not forwarding packets to this router anymore, which is obviously a good housekeeping rule. Now next we can process our host routes, and obviously that's not selected by default. Now this option is going to process routes to individual hosts on our network rather than routes to network segments. And include host routes will then include these routes in the updates to other routers. Now we can also do the same thing for our default routes, and of course these are the networks that this router is directly connected to. And we've seen these default routes working when we first installed our router. Now right at the bottom we've got one final option, disable subnet summarization, and this option stops the router from summarizing the subnet or the class ID of the subnet and sending that out. Alright, so that's all the options. Everything's already configured. We're going to leave it as it is, so we'll click OK. And there's our interface that's now being configured. So let's go and hit refresh a couple of times, and hopefully our router will have contacted any other routers that I have in my network and will have gotten some updates. Okay, so it's sent out a few responses, and let's just refresh this a couple more times and just see if we can get some responses received. All right, and there you go now. We've now got a couple of responses sent and received, which is indicating to me that our routers are now talking. This router is now talking with any other routers that I've got on this network, and these routers, thanks to the RIP protocol, are now sharing all of the routers, or all of the routes rather, that they know about each other automatically. So if we go and right click on static routes and choose to show the IP routing table, let's expand this out fully, we'll be able to see right here that we've got this update that's come from our RIP router. It tells us that if we want to get to the 10.96 network, then we need to talk to the 10.64.0.3 network interface in order to get there. And that's great because we didn't manually have to enter in this route. We didn't even have to find out that it exists. Simply by sharing these route tables, RIP has done all of the work for us. Okay, so there you can see that configuring RIP is not a terribly difficult thing to do. But whilst most companies are still probably going to opt for a hardware router solution from companies like Cisco, it's nice to know that you do have a very functional and easy to configure router built right into your Windows Server 2008 operating system. So in this video, we've talked about how we can configure routing on a Windows 2008 server. So by now, you should know how to install the routing and remote access role and configure both static and dynamic routing. So we hope you've enjoyed this video and would like to thank you for watching.